Yes, good morning. Here in this class, we will do some arithmetic computations using the procedures we have learned in the last few classes. Okay. So I have taken these exercises on addition and subtraction to give you clarity on the procedure for adding and subtracting the signed magnitude numbers and 2's complement numbers. Okay, here the question is, first question is, mark each individual path in the flowchart by a number. And then, so we have seen for adding and subtracting signed magnitude numbers, the flowchart. Okay, you have to recollect the flowchart. Here we have seen there are different paths, right? If it is addition, you will have two paths. And if it is subtraction, there are again two paths, okay, depending on the sign, as it is signed magnitude representation. Depending on the sign, okay, when you do perform this exclusive OR, this may be 1, the result may be 1 or 0, depending on that, it will take the path. So the question is, you need to mark the individual path in the flowchart by a number and then indicate the overall path that the algorithm takes when the following signed magnitude numbers are computed. In each case, give the value of AVF. Okay, you have to give the value of AVF. First, mark the individual path in the flowchart and then, okay, find the path that this particular, the algorithm takes when this particular computation is done. Okay, the leftmost bit in the following number is the sign bit. Signed magnitude numbers, we have the leftmost bit as sign bits. Let's take the first one, 0, 1, 0, 1, 1, 0, 1. Here only we'll do 0, 1, 1, 1, 0, 1, 1, 0, 1. And the second number is 0, 0 followed by 5 ones plus 0, 0 followed by 5 ones. So here 0 is a sign bit, and in this second number 0 is again a sign bit. So this indicates that both the numbers are positive. Okay, and what is the operation given here? It is addition. Okay, the operation here is to perform addition. So which part? Here, this in the flowchart, we go to this addition, add operation. And before that, let's number the path. Here, let's say there are 4 paths. This is path 1, and this is path 2, this is path 3, and 4. Okay. Now, as this is add operation, we take this particular part of the flowchart, and here A is in augend is in A and addend in B. A is the first number and B is the second number, and AS and BS. This is our AS. Okay, in our question here, AS is the sign bit of A and BS is the sign bit of B, and let's take this as A and the second number in B, the magnitude in A and B and the signs in AS and BS. So first we do exclusive OR. We perform exclusive OR on AS and BS. So if the signs are same, it produces 0. If the signs are different, it's an odd function. It produces 1. So here in our case, the signs are 0 and 0. So it must be, okay, the value, the result of this XOR must be 0. So the path it takes is 1. Okay. So what is this path 1? What is the operation we need to do here? EA is equal to A plus B. Okay, so what we do here is EA is A plus B. What is A? 1, 0, 1, 1, 0, 1. And B is 0, 1, 1, 1, 1, 1. When you add, 1 plus 1 is 1, 0, 1, 0. 1 plus 1 plus 1 is 1, 1. Again 3 ones, 1, 1. 1, 0, 1, 0, 1. Okay, now the carry is 1. So what is the next step? The next step says store E. Okay, this is our E, carry E. EA is 1, okay, with the carry, and this is our A, the final result. Okay, and AVF is E. We store E into AVF. AVF. AVF is E. E is 1. Okay. So as this is 1, okay, we say that there is overflow. Okay, during addition, if you see the representations here, what is 1, 0? The first number I'm taking 1, 0, 1, 1, 0, 1. It is 2 power 0, 2 power 1, 2 power 2, 3, 4, and 2 power 5. 32 plus 8 plus 4 plus 1 is 45. Okay, this is our first number. And the second number is 0, 1, 1, 1, 1, 1. 2 power 0, 2 power 1, 2 power 2, 2 power 3, and 2 power 4. 16 plus 8 plus 4 plus 2 plus 1 is 31. Okay, our second number. When you add 45 and 31, you must be getting 76. Okay, we have overflow here, so the result we are not checking. It is not correct result. We will not get the correct result when there is overflow. Okay, so here AVF is 1 and the path it takes is 1. Okay, in the flowchart, it takes the first path and the numbers are added and you get overflow here, that is E. E is considered as overflow, that is stored in AVF, and the result as it is sent to the sent. This is our first example. And let's take the second one. One subtraction operation we'll take for let's take the second problem. 0, 1, 0, 1, 1, 0, 1 minus 0, 0, 1, 1, 1, 1, 1. This is A and this is B. The sign bit of A is in AS, register AS, and sign bit of B is in BS. Okay. Now the operation you need to note here, it is subtraction. So we take this part of our algorithm and minuend in A, subtrahend in B. Okay. And we perform the exclusive OR operation on AS and BS. AS is 0, BS is 0. So what is the path it takes here? Okay, as this is 1, second, third path, and 4. So here it is subtraction. As the sign bits are same, it takes this path. Correct? Path 4. The result would be 0. It takes 4. And here, what is the operation to be performed? EA is A plus B complement plus 1. That is 2's complement of B. Okay, let's find the 2's complement of B. It is 0. The number is 0, 1, 1, all ones. So the 2's complement would be 1, 0, 0, 0, 0, 0. And when you add 1, you get 1, 0, 0, 0, 0, 1. This is the 2's complement of B, B complement plus 1. Now, if we need to add this to A, as it is subtraction, the step is A plus B complement. Okay, 1, 0, 1, 1, 0, 1. When you add this, 1, 0, 0, 0, 0, 1, you get 1, 0, 1, 1, 1, 0, 1 plus 1 is 1, 0 with a carry E. Carry E is 1. Now check, this number is 101101. Okay, we already checked. It is 45. Okay, the first number 101101 is 45, and the second number 011111 is 31. Okay, And the operation we performed here is 45 minus 31. It is 14. Okay, the result must be plus 14. And here AVF is 0. Okay, as it is subtraction, the flow chart, look at the flow chart here. We perform this function, this operation A plus B complement, and we set AVF as 0. Okay, there is no overflow here. Okay, as it is subtraction, by default AVF is set as 0. And the next step is we check the carry. Okay, E. If E is 1, okay, here our E is, the value of E is 1. If A is 1, that means A is greater than B. Okay, so when we perform subtraction, if A is greater than B, performing A plus 2's complement of B is correct. Okay, so we consider this A as the result. So if A is greater than B, so we take this path here and we check A is 0 or not 0. It is not 0. Okay, this is our A result. So we consider it as a result. So the result must be correct here. If we check it, the result is 0, 1, 1, 1, 0. Okay, it is 0, 0, 1, 1, 1, 0, 2 power 1, 2 power 2, 2 power 3, 8 plus 4 plus 2. It is 14. Okay, and the sign bit is 0. It says it is positive. So the result is plus 14. Okay, as there is no overflow, we get the correct answer in subtraction here. So we check this path. Okay, one addition we performed which took this path 1, and we also check this. Now the number should be, we need to take two numbers with two different signs. Okay, one addition, we'll perform one addition and subtraction. So let's now change this. We'll take the question here. We don't have. Okay, here again you will get the same, it's the same kind of operation. Okay, for these two also. So let me take path 1, 2, 3 and 4. So the third number we take must be with two different signs. So let me take 1, 0, 1, 1, 1, 1, 1, the same number, 31 minus 0, 0, 1, 0, 1, 1, 0, 1. So in this case, this is AS and A, BS, the sign bit of B, and this is B. Okay, now let's compare the sign bits. This is subtraction. The operation here is subtraction. So we take this part of our algorithm. We begin with this part and perform AS exclusive or BS. What it gives, the result would be 1. Okay, so the path we take here is 3. So if the sign bits are different and the result of this XOR is 1, means, okay, the path 3 is add A plus B. Again, we add here, we get overflow. Okay, the operation we perform is A is equal to A plus B. A is 0, 1, 1, 1, 1, 1. B is 1, 0, 1, 1, 0, 1. We already did this. 0, 1, 1, 0, 1, 1, 1, 1, 1, 0. Okay, so we consider here ES overflow. AVF is 1. And this is EA. Okay, EA is 1 with the carry. E is 1 and the result is 0, 0, 1, 1, 0, 1, 0, 0, and AVF is 1 and there is overflow. Okay, so this is our result. Okay, now let's take the fourth case. We take two different numbers. okay, with two different signs to check this part of the algorithm, okay, to understand this part where A is less than B. Okay, so our first number, we'll take the first number, okay, that is smaller than the second number. Let's take 0, yes, 0, 1, 1, 1, 1, 1 minus 0, 1, 0, 1, 1, 0, 1. Okay, so this number, the decimal representation is 31 and this is 45. And here is AS and A. This is BS, sign bit, and this is B. Okay, now the operation to be performed is subtraction. So we begin with this. And here we check the sign bits, AS and BS, okay, exclusive odd, give us 0 because the sign bits are 0 and 0, 0, 0, okay, when exclusive odd give us 0. So the path it takes is this path, 4. Okay, so here what we do, EA is equal to the operation to be performed is EA is equal to A plus B complement plus 1. Okay, B is 1 0 1 1 0 1. Let's find the 2's complement of B. 0 1 0 0 1 0 plus 1 0 1 0 0 1 1. Okay, this is the 2's complement of B. And to add to A, 0 1 1 1 1 1 and 0 1 0 0 1 1. When you add 1 0 1 1 1 0 1 0 1 1 and here 1, correct? So this is our result. Now if you check what is E here, it is 0. Okay, the carry is 0. Now we need to, and we set AVF is 0. Okay, there will not be overflow. This is subtraction operation. When this particular operation is performed, there won't be overflow. We assume that there will not be a overflow. Okay, and we set AVF is 0. Okay, AVF is set to 0. Now the next step is to check E. When you check E, you get the value of E is 0. There is no carry here. Okay, it is 0. That means the number we took as a first number, A, is less than B. Okay, so for subtraction, but the bigger number has to be, smaller number has to be subtracted from the bigger number, whereas we performed subtraction of bigger number from the smaller number. Okay, so what we do is we invert the result. Now A is equal to A complement. Okay, we find the complement and A is equal to A plus 1. That means find the 2's complement of A. A is our result now. Okay, invert the bits. Okay, this step is finding 1's complement of A and then adding 1 to it, that is finding 2's complement. So when you invert the bits, 0 0 1 1 0 1. When you add 1 to this, 1 0 1 here, 1 1 0 0. Okay, and what is the sign? The next set step says AS is complement of AS. Okay, what is AS? AS is 0 here. Okay, so you need to invert that also. So that becomes AS becomes 1. The sign is 1. Now what is this number? 2 power 1, 2 power 2, 2 power 3. It is 8 plus 4 plus 2 is 14. Okay, and the sign is 1. So we say the result is minus 14. Correct? 31 minus 35. 31 minus 45 is minus 14. Okay. Okay, when A is less than B, here we have taken the number to understand this part. We have taken a number, okay, A that is smaller than B. So that case you get E as 0. The carry will be 0. Okay, that means A is less than B. So what we do, we invert the bits of A and find the 2's complement. Then also we also invert the sign bit. And the second question here. Now perform the arithmetic operations with binary numbers and with negative numbers in signed 2's complement representation. Okay, so negative numbers should be in 2's complement representation. And use 7 bits to accommodate each number together with its sign. In each case, determine if an overflow by checking the carries into and carries out of the sign bit position. So what we do, we perform these operations, these two operations, and then we check if there is a overflow. Okay, if in signed 2's complement representation means the negative numbers. If there is a negative number, it need to be 2's complemented. And here it is subtraction. Again, we take the 2's complement of the subtrahend. Okay, so let's take the first problem here, and the flow chart is this, correct? For 2's complement addition and subtraction. The first one is 35 plus 40. Okay, both the numbers are positive. Plus 35 plus 40. So we need to find the binary equivalent of 35. How we find? Just convert this to binary. 1, 7 2s are 14, 8 2s are 16, 4, 0, 0, 2, 1, 0, 2, 0, 1. So 35 is written as 1 0 0 0 1 1. Okay, we take the numbers in this order. Okay, from down, the first, this is the most significant bit. So 1 0 0 0 1 1 plus second number is 40. Okay, find the binary equivalent. 20, 10, 5, 2, 0, and here 1. So we take it this way, 1, second number is 1 0 1 3 zeros, 1 0 1 3 zeros. Okay, this is 40. Now the question is, use 7 bits, okay, to accommodate each number together with its sign. Here we have 6 bits. Okay, so we take the sign bit as sign is 0. It is plus 35, 0, and this is 0. And you need to remember that this is 2's complement addition and subtraction. Okay, in signed magnitude representations, we take sign bit, sign of A in AS and sign of B in BS. Here sign bits are considered with the other number. Okay, we will add and subtract. Okay, we perform the other operations with the other numbers. So here to add now, it is 0 1 0 0 0 1 1, and the second number is 0 1 0 1 0 0 0. Okay, we perform addition 1 1 0 1 0 1 0. The carry is 1 here, and 0. No, sorry, it is 1. It's 1, and the carry is 0. Okay, what the question is, in each case, determine if there is an overflow by checking the carries into and out of the sign bit position. What is the carry in? Carry into the sign bit is 1, and carry out of the sign bit is 0. C in is 1 and C out is, okay, carry out is 0. So when the carry in and carry in out are different, right? If they are same, we say that there is no overflow. When carry in and carry out are different, there is overflow. Okay, it is addition. So we are performing this operation in the flow chart. AC is AC plus B. We added both, and the overflow is taken in B. Okay, or we take AVF. Okay, the register AVF, add overflow. Okay. So the question is to determine if there is an overflow. Here C in is 1 and C out is 0. So there is overflow. Okay, C in is not equal to C out. Okay, so you can say there is overflow. So even if you check the result, it is not correct. You see here we have added two positive numbers and the result you got is a negative number. Okay, the sign bit is 1. Okay, this is not correct number because there is a overflow. We are proving that yeah, C in is not equal to C out. The carries off, so there is overflow. And the second question, 40 minus 35. 40 plus 40 minus plus 35. What is 40? We wrote it 40 is 101000 minus plus 35. What we found is 100011. Okay, and the sign bit is 0 here. This is 0. Now when we perform subtraction, 0 1 0 1 0 0 0, and as here it is subtraction, what we do, we find the 2's complement of B. Okay, this is A and this is B. So B complement plus 1. 1 0 1 1 1 0 0. Add 1 to that, 1 0 1 1 1 0 1. Now when we add this to the this to A, 1 0 1 1 1 0 1, we get 1 0 1 1 0 1 0, 1 plus 1 again 1 0, 1 0, carry in is 1 now, 1 plus 1 1 0, carry is 1. Now see the carry in and carry out of the sign bit. Okay, what is C in is 1 and C out is also 1. Okay, when the bits C carry in and carry out are same. Okay, C in is equal to C out. Okay, no overflow. There won't be overflow. So now let's check the result. It is 1 0 1. Correct? 0 0 0 0 0. Here the sign is positive. Okay, so that means the result is positive number and it is 101. 101 is 5. Okay, and here 40 minus 35 is 5. So this is how, okay, addition and subtraction on signed magnitude numbers and this signed 2's complement numbers are performed. Hope you have understood the flow of the process. Okay, this class I have specially taken to make you understand the flow of the process. Okay, taking a number and which path of this flowchart it will take. Okay, and which process is performed and how the result is obtained. Here is a flowchart for multiplication. This is a flowchart for multiplying two signed magnitude numbers, and we have both multiplication algorithm for multiplying two signed 2's complement numbers in 2's complement form. Correct? Okay, and division. Both multiplication, I think we have already taken few examples. I have explained it, and division also yesterday we have worked with a few examples. So now this multiplication is to perform multiplication on signed magnitude numbers. Let me explain with one example. So let me take the numbers 15 into 5. Okay, here what we do, AS is, okay, the resultant sign of the result is AS, that is QS exclusive or BS. Okay, the two signs are taken, B and Q. Now QS and BS, okay, the sign bits are taken. We need to convert it to binary first and then we take the sign bits in AS and QS, and then A is initialized to 0, E is 0, E is the carry, SE is to check how, to keep a count on how many times we need to repeat this process. Okay, initially it will be set to the value of n. N is the number of bits in the multiplier. And what we repeat, every time we check Qn, the last bit of the multiplier, the least significant bit of the multiplier. And if it is 1, we perform addition. We add B2 because multiplication is implemented as repeated addition, right? And every time when Qn is 1, we add B to A. When Qn is 0 means the multiplier bit is 0. When the multiplier bit is 0, we don't have to. 0 into 0 multiplied by anything becomes 0. Okay, so what we do, we just shift right. Okay, shift right is performed after every operation, and then we decrement SC, and we repeat this process until the value of SC becomes 0. Okay, so let's take this number. What is 15? So B here is 15, that is 0, 1, 1, 1, right? And 5 is, Q is 5. It is, I'm taking 5 bits. Okay, let's assume that we are storing these data in 5-bit register. So 0, 0, 1, 0, 1. 5 is 1, 0, 1. And here is a sign bit. So here this is our BS and this is QS. Now let's write this table E and A, Q, SC. E is initialized to 0. Okay, we are here in the initialization part. If you see, A is initialized to 0. It's 5 bits. And Q is the multiplier. The multiplier here is 0, 0, 1, 0, 1. And SC is set to the number of multiplier bits. Okay, number of bits in the multiplier are 5. So we set it as 5. Okay, and the first process is, we need to check Qn. What is Qn? Qn is 1. Okay. So when Qn is 1, what we do? We add B to A. A is here and B is 0, 1, 1, 1, 1. When you add this, you get 0, 1, 1, 1, 1. Correct? And the next operation is, after performing, we perform shift right. Okay, so when you shift right, what we get? Here is 0, carry is 0. So when we perform shift right, this moves to this 0 and 1, 1, 1. And this 1 moves there, 1, 0, 0, 1, 0. Okay. Now, AC is decremented, it is 4. And the second step, again check Qn. What is Qn now? It is 0. When Qn is 0, we will not add. Okay, check the flow chart. When Qn is 0, okay, this part. When Qn is 0, we just shift right. So what we perform here, shift right operation. When we shift right, it is 0 and these 4 bits, 0, 0, 1, 1. This is shifted to right. So 1, 1, 0, 0, 1. And it is decremented to 3. Next, the third step, again check Qn. What is Qn? It is 1 here. So we need to add B. Okay. When Qn is 1, we add. What is B? 0, 1, 1, 1, 1. When we add 1, 0, 1, 1, 1, 0, 1, 0, 1 with the carry 0. The next operation is shift right. When we shift right, 0, 1, 0, 0, 1 and this 0, 1, 1, 0, 0 and decrement SC 0, 1, 0, it is 2. The next step is again check Qn. Qn is 0 now. So only perform shift right. 0, move it 1 bit right. 0, 1, 0, 0. And this 1 here, 1, 1, 1, 0. no, 1, 1, 0, 1, 1, 0. Okay, so when you decrement this 1, the next step is check Qn again, it is 0, so shift right. When you shift right, 0, 0, 0, 1, 0, the 0 here, 0, 1, 0, 1, 1. This we decrement, it is 0. We stop the procedure when SC becomes 0. Okay, so what is this? Now this will be our result. Okay, as it is multiplication, the result may occupy more bits. Okay, so that is the reason we are taking 2 registers, A and Q, to accommodate the result. Okay, now if you check this, what is this? 2 power 0, 2 power 1, 2 power 2, 2 power 3, 4, 5, and 2 power 6. So when you add this, you get 2 power 6 is 64 plus 8 plus 2 plus 1, which is 75. Correct? And the sign bit is 0 here, so it is plus 75. And you can check this decimal numbers. 15 into 5 is 75. It is positive 75. Okay, so here you need to first understand the flow. Okay, flow of the process, and you have to write this E. Okay, if question is given to show the contents of register E, A, Q, SC, okay, for the successive operations performed for multiplication on signed magnitude numbers. What you will do, you will draw the flow chart and write these values, okay, E, A, Q, and SC, the registers, and fill it with, initially you initialize it as 0 and then perform these process, okay, what is there in the flow chart. We check Qn. First step is we check Qn. If Qn is 1, we add B to A. If and shift right. Okay, after that we shift right and decrement SC. That is one step. If suppose the other possibility is Qn may be 0. If it is 0, we will not add B to A, we will just perform shift right. Okay, and then decrement SC. Repeat this process until SC is 0. And what you get finally in register A and Q, okay, combined together is the result. Any doubts in this addition, subtraction, and multiplication? We also discussed both multiplication in earlier class and then division. We have already taken enough examples for that. Now, okay, this is your assignment. In multiplication and division, what we have seen here in this question is multiplying the two sign magnitude numbers, and here you have two complement numbers. Okay, show the step-by-step multiplication process using Booth algorithm when the following binary numbers are multiplied. Assume 5-bit registers that hold the signed numbers. Okay, these are the two numbers, and Booth multiplication algorithm is meant for 2's complement multiplication. So you find the binary equivalent. You write E, A, register Q, and SC. Okay, this is how you show the step-by-step procedure. Okay, the process, multiplication process. And the first step, okay, here in Booth multiplication algorithm, we check Qn and Q naught and Q minus 1. You remember? Q naught and Q minus 1, the last 2 bits of the multiplier. Okay, there are 4 possibilities. It may be from 1 to 0 or 0 to 1. Upon encountering 1, you subtract, and upon encountering 0, you add. So there is subtraction. Okay, you need to find the 2's complement of 13 for subtraction, means adding it to A. Okay, you check the earlier exercises. We did it already. Okay, and follow the same and show the step-by-step procedure and bring the result, show the final result. And the second question is show the contents of registers EAQs during the process of division. Okay, what we saw in the last class. The numbers given are, this is our dividend, okay, and this is the divisor 0011. Okay, we learned the algorithm. You have to show the registers E, A, Q, and SC. Here we perform left shift. In division, we perform shift left, correct? Okay, follow that procedure and complete this. With the earlier questions, you can do these two also. Any doubts?